to make the. All right, we are being recorded. Today we will have Eric Perlmutter, who will speak about what's on the screen right now. So go ahead, Eric.
Fabulous introduction. Thank you, Walt. It's true, I will speak about what's on the screen. Thank you for the opportunity to give the talk. It's a shame I can't be giving the talk in person at Bootstrap University, but such are these difficult times. And in difficult times, n=4 super-Yang-Mills is there for you. So this is based on a paper that came out a few weeks ago with Scott Collier, who may be in the audience, although I think he's got to go at some point, who's a postdoc at Princeton. And so let me hide that. Good. All right. So what's the talk about? It's really about two topics: S-duality in n=4 super-Yang-Mills and the status of holographic duality with type 2B string theory. To essentially just quote from the beginning of our paper, there are two goals of the paper and two goals of the talk. The first is to understand how to extract the full implications of S-duality for n=4 super-Yang-Mills observables, perhaps with generalizations to other conformal field theories later. And second of all, to reframe the ADS-CFT correspondence with these insights, namely the traditional one between n=4 super-Yang-Mills and type 2B string theory and ADS5 times S5. Let me introduce a few elements that we'll need, although of course n=4 is a exciting, important theory. There's lots going on, but what we'll need is essentially the following. There is a gauge group. There's a complexified gauge coupling, tau, parameterized by G Yang-Mills, which I'm just calling G, and the theta angle, which can be combined in this way, as is conventional. Being exactly marginal, tau parameterizes the conformal manifold, and in particular, the conformal manifold that preserves the full supersymmetry is one complex dimensional. And I've pictured it here as this teardrop-like region with this cusp up here corresponding to the G=0 limit. Now, n=4 super-Yang-Mills enjoys S-duality. When the gauge group is simply laced, this is a self-duality, and in particular, it's SL2Z invariant. So in the theory, non-perturbatively well-defined observables obey the following equation. Under SL2Z transformations of tau, they go back to themselves. There are some extended objects which are not self-dual, but I'm not talking about those. One can understand those subtleties by looking at some nice references by Aharoni, Fujikawa, Seiberg, and some others. So in light of this, one can restrict tau to the fundamental domain of SL2Z, which I've drawn here. Now, the existence of S-duality itself is beyond a reasonable doubt, I would say. There have been lots of checks from field theory and from holography and its duality with type 2B string theory. On the string theory side, strings in 10D flat space are believed to admit an SL2Z symmetry, which acts on the complexified tau, here the complexified string coupling, e to the minus phi here, and that's the axion. And ADS5 times S5 preserves this symmetry. Apart from some large N results, though, the explicit modular structure of the observables in n=4, say conformal dimensions or OP coefficients or correlators, is an open question. And it's a hard question because, first of all, S-duality is inherently non-perturbative. It's a statement about weak strong duality. And in particular, if you want to understand the modular structure of something, you need to contend with knowing it for intermediate values of tau, say G of order 1, and that's hard. In addition, in the Tuff limit, say in the planar theory where integrability rules, S-duality is obscured. So it's also hard to see it analytically in that regime. The conformal bootstrap, for all it's done for n=4 super-Yang-Mills, has left S-duality largely unexplored, I would say. And it's for these reasons given above. Numerically, of course, the bootstrap is capable of non-perturbative insights, but you'd be hard-pressed to stare at a numerical plot and write down the modular function which describes the tau dependence of that observable. And then analytically, if you want to get exact results, say at finite n, then you're back to the problem that this is a non-perturbative question. These references here, of course, made great progress. This first reference set of references tried to understand interpolating functions across the conformal manifold, across moduli space, in an S-duality invariant way. But as they discussed, there were some ambiguities in how exactly one does that, which reflects the fact that it's hard to know how to constrain even the space of modular functions that these SCFT observables can realize. This recent work by Chester, Dempsey, and Pufu has some beautiful constraints on =4 data, say for SU2, but the modular structure there is very unclear because the plots ultimately are numeric. So the point of view here is that there's an opportunity. N=4 super Yang-Mills enjoys a symmetry that we've not fully used. And so what does it mean to use it? Well, one answer that's familiar to this crowd is to systematically incorporate the symmetry from the beginning of calculations, which reduces the observables to their non-symmetry determined data. And that's the essential data that characterizes the observable and in turn the theory. So our goal is to try to do that. And the idea for how to do that is to import some spectral technology for SL2Z from the math literature. This is a robust tool. It applies at finite n and for any S-duality invariant observable. And as we'll see, it gives a very different presentation of N=4 super Yang-Mills than what is usually done. And so that's part of why I feel that there's promise in applying this further. And some examples that we'll treat show that already it's capable of simplifying very nicely. So besides the fact that it feels conceptually like a good thing to do as a theoretical physicist to use symmetry in an efficient way, we find some intriguing structures falling out in the examples we study, and some very direct derivations of the existence of non-perturbative phenomena using relatively elementary calculations once the framework is in place. At large n, in the expansion around strong TÜV coupling, as we all know, N=4 super Yang-Mills is famously dual to type 2b supergravity in a DS5 times S5 with a prescribed set of stringy corrections. And remarkably, the story that we're going to tell has something new to say about this. And that result can be stated as follows, to be justified and explained later. Given some observable O on the level of individual observables O, the large n limit of ensemble averaged N=4 super Yang-Mills is the strong coupling limit of the planar theory, that is to say, the supergravity limit. You can think of this in the following way. This is a figure. On the right, we're averaging over the moduli space at finite n and then taking the large n limit. And on the left, we're taking large n and then taking g to 0, or if you like, taking the TÜV limit where you approach the cusp and taking large lambda. And these two theories at the level of the observables are equivalent. So we find an emergence of ensemble averaging in this traditional holographic duality. And this is intriguing and not something we completely understand the consequences of, but it embeds averaging in the usual story in a kind of nice way. So that's the big picture. The outline for the rest of the talk is as follows. First, I'll introduce this spectral theory to which I alluded. And now's a good time to emphasize that I first came upon this in a project that resulted in a paper from last summer with Liam Fitzpatrick, Alex Maloney, Nathan Benjamin, and Scott Collier. Well, there we applied it in the case of 2D CFT partition functions. And I talked about it over the summer at Bootstrap 2021. But I think this technology actually works much more sort of cleanly in this setting, as I'll try to explain. Then I'll explain why this technology and how it applies to observables of N=4 super Yang-Mills. We'll move on to constraining the observables of N=4 in this language. This will lead to some nice results about instanton physics and a very nice set of insights, I would say, regarding this beautiful object that was studied by Doragoni, Green, and Wen, which is an integrated 4-point function of the 20 prime, for which they have some conjectural expression as a function of n and tau. And we'll be able to explain and elucidate their expression rather directly. At large n, we'll go to the TÜV limit, we'll find some non-perturbative physics, and this will lead us right to the statement of supergravity as SL2Z average strings. And in turn, we'll study the ensemble of n equals 4 theories, which I'll call the SL2Z ensemble, and the statistics thereof, and some remarks on what this implies for radius CFT at large. And then I'll conclude with some future directions. So just a couple conventions. I'm going to write things as functions of tau, but everything depends non-holomorphically on tau, despite appearances. And with apologies to Henri Poincaré, all French accents are set to 1 throughout the talk. So good. So let me try to give a sort of high-level overview of what the spectral theory is. And it really boils down to the statement that a square integrable SL2Z invariant function admits a unique decomposition into an SL2Z invariant eigenbasis of the Laplacian on the upper half plane. So the decomposition takes the following form. If we have some observable O of tau, again, non-holomorphic, there's a constant piece, there's a continuous branch, and there's a discrete branch. This is a non-holomorphic Eisenstein series, which is well studied. This is what's known as a Moss-Cusp form, which are less well studied by us, physicists, but very well studied, though still elusive, by mathematicians. Here's a plot, a picture of what this decomposition looks like in essence. There are 4 lines. The red one is the square of one of these real analytic Eisenstein series, where I've squared it to get all the Fourier coefficients involved. And I've just chosen some value on this critical line where the real part is a half. Okay, so I've just taken its index to be a half plus I.
Hi, Eric, we don't see your pointer moving. It's stuck.
Yeah, I just noticed that. Well, let's see. I don't know what to say. I sure see it, but it's not critical. So perhaps we move on.
Okay.
All right. Sorry about that. Okay, good. So there's an Eisenstein piece, and then I've plotted 3 of these Moss-Cusp forms, these discrete members, and I've restricted all these to the 0 modes in the Fourier decomposition. So they're functions of y, where I'm taking y to be the imaginary part of tau. So throughout the talk, tau equals x plus iy. Okay. And again, I've squared them so that all Fourier coefficients of all the modes are involved here. Obviously, the red curve is quite smooth, whereas the yellow, green, and blue curves are a bit sporadic. They oscillate. They have extrema at what seem like random places, and they don't particularly look like one another. That reflects the fact that these cusp forms are known to exhibit what's called arithmetic chaos, whereas the Eisenstein series are these classical objects which are very nice and smooth and don't have this property. Indeed, the math of these cusp forms is an active area of research, and this notion of arithmetic chaos is something that mathematicians have various conjectures about and are continually trying to understand and update their understanding of. So let's say a little bit more about this without really trying to get bogged down, because I want to make sure that the physics, the implications, is at the forefront of the talk. So first, there's a constant piece. Okay, this is what we're going to call the modular average. It's just the integral of O over the fundamental domain with the Poincaré measure. And every time you see an inner product, it's with respect to this measure. Okay. Remember that the volume of the fundamental domain is finite, even though it's non-compact. So there's some volume factor here for normalization's sake, so that the average of 1 is 1. Very well. So there's the continuous piece, which is comprised of the Eisenstein series on the critical line, real part of S equals a half. These are eigenfunctions of the Laplacian delta t with this eigenvalue. The Fourier decomposition, we'll return to it later. Here it is. There's a 0 mode and a non-zero mode, where the modes are labeled by k in this talk. The 0 mode has 2 power law pieces in y, where I remind you for the last time that y is the imaginary part of tau. Of course, please ask if I should be updating you more often on this. And then the Bessel function dependence here is rather simple with some number theoretic coefficient, the divisor sigma, and so on. The overlap of O with the Eisenstein series can be expressed as a Mellin integral of just the 0 mode of O. with this parameter s hiding in the integrand. And here I've introduced this curly bracket just to, for the sake of elucidating the symmetry. When you form this starred Eisenstein series, known as the completed Eisenstein series, where you multiply by this lambda factor, which itself is called the completed Riemann zeta function, then the Eisenstein series admits an s goes to 1 minus s symmetry, and so likewise does the rescaled overlap, which I have to define with this brackets. Okay, so it obeys a functional equation, s goes to 1 minus s. And during the talk, I'll refer to that as reflection symmetry.
So can you, Eric, can you explain this equation, why the overlap involves just the average? So I remember this already came up a year ago in your...
Why the overlap just involves the zero mode?
Yeah.
Okay. Yes, so the Eisenstein series admits a Poincare series representation. And there's something called the unfolding trick, which allows you to take this integral over the fundamental domain. And upon inserting this Poincare representation, trading the x integral in such a way that you just restrict the x integral to the zero mode. So all that's left is a y integral, and the x integral, after using this representation, just reduces to the zero mode. So it's a special property of the fact that you're integrating against the Eisenstein series. In general, this is not what an inner product.
So what goes into this? That O is
nothing goes into this with respect to O. So it's really O is anything here, and you're using a nice property of the Eisenstein series to take this two-dimensional integral, the inner product, and do the integral over the real part of tau. Turns out this isolates the zero mode of O, and all you're left with is the integral of the imaginary part of tau. And instead of running from, so now you've created the fundamental domain for the strip, and you do the x integral, and after that you have the y integral all the way down from the real axis up to infinity, and that's what this is.
So in particular, we have not imposed that O is modular. This is a completely general decomposition.
We've not imposed that O is modular in making the equivalence between the overlap and this Mellin integral. Of course, the existence of the decomposition assumes that O is modular, but that step, that's right.
But I'm confused at step 0. So if I have a function on an interval, I can Fourier decompose it. It doesn't mean that the function is periodic.
Mm-hmm.
So if I have a function defined in the full upper half plane, I can just do this integral on the modular domain, and surely it will converge. It doesn't mean that the function is actually modular. I mean, something about boundary condition must be said somewhere,
right? Sure. Well, boundary conditions are relevant for convergence of this integral, for example. But I mean,
what about the
modularity is not appearing? Is not.
If I have a function finding the interval on the real interval between 0 and 1, I can expand it in sines and cosines, but each of the terms of the series is periodic, but it doesn't mean that the function is periodic. I mean, why is the analogy with Fourier series not correct?
I think a quick answer is that for the unfolding trick to work, you're using the fact that the Eisenstein series is a sum over modular images. And that reduces to an integral over the strip, say the strip with unit width, if O is modular invariant. If it's not, then I don't think the unfolding trick reduces to an integral over the strip.
I think there's no loss of generality here to restrict the whole discussion to modular invariance O, because we can take any function O in the modular domain and just extend it.
Exactly.
Extend it, and at this point, O is just some L2 integrable function. There is no continuity or anything. So,
yeah, that was my complaint.
Yeah.
Shall we proceed?
I guess so, yeah.
All right. Sorry, good. Okay. So the third element, these cusp forms are wilder. They too are eigenfunctions. They're infinite in number, and there's an asymptotic Weil's law that governs their density. The fact that they exist is not trivial because the fundamental domain is not compact, but it has finite volume, and ultimately that's what's responsible for their existence. There are similarities and differences with the Eisenstein series, mainly differences. There's no zero mode. These are the Fourier coefficients. This is some normalization, the A1 tilde. I assume you still can't see my pointer. Is that right? All right. And because there's no zero mode, they decay exponentially at the cusp up at infinity. Not one of the eigenvalues or Fourier coefficients is known explicitly. And this ultimately boils down to their chaotic nature. But for at small n, and not very small n, just many hundreds of thousands of values of n, the first thousands of these, they're extremely precise numerics, both for their eigenvalues and for their Fourier coefficients. And at large n, for the asymptotically large eigenvalue cusp forms, there have been observed many ergodic universal behaviors, which all go under the umbrella of what is sometimes known as the random wave conjecture, all of which is part of this story about arithmetic chaos. So at small n, a lot is known, but not even one of these is known exactly. At large n, a lot is known and believed to be true. And so there's some decent landscape of understanding of these, but it's not analytic. Okay, so back to n equals 4. Well-defined CFT observables are finite for all values of the coupling, except for possible divergences at boundaries of moduli space. Now, in n equals 4, the cusp is just the free theory, and so observables converge to their free values there. If somehow you're considering something which does not converge to a finite value, just renormalize it, subtract that off, and that resulting quantity is still SL2C invariant. And as a result of this, this fact is square integrable. Therefore, n equals 4 superangular observables admit a spectral decomposition. That's one of the main points of the talk. So without doing so much, there are a couple implications that come for free, so to speak. The first is that instanton physics is highly redundant. The Fourier decomposition of an n equals 4 observable is the decomposition into instanton numbers. So k is the total instanton number, where you can have instanton and anti-instanton pairs for any k, but if you add up in a given term, say the total numbers of q's and q bars, take their difference, that's the total instanton number k. And the statement implied by the spectral decomposition is that instanton sectors for k greater than 1 are uniquely determined in principle by the 0 and 1 instanton sectors. The argument is the same argument that we gave for something called spectral determinacy in the context of 2D CFTs. So we said before that using the 0 mode, you can uniquely reconstruct the Eisenstein part of the decomposition. So given the 0 mode, you construct the continuous part. You subtract that off, and then if you're trying to construct the k equals 1 mode, you can do this by inverting the Fourier decomposition of the cusp forms. Now, this is partly just something that is true in principle, because as I said, the eigenvalues for the cusp forms, and then in turn, the labels for these Bessel functions are only known numerically. But the decomposition exists, and that's sufficient to make this statement. So that's surprising. The second implication is the following. In a general CFT, we can define the ensemble average over a conformal manifold with respect to, say, the Zamolodchikov measure, defined by the 2-point functions of exactly marginal operators, in the following way. You integrate over the conformal manifold parameterized here by some moduli x. So you take some O, it depends on x. You
I'm sorry,
over the manifold.
I got confused at this point. So
yeah,
could you go back, please, the slide where you showed the cusp form? So I'm a bit confused how you can, what exactly you need to integrate to recover this QKs. So here's the cusp form. Okay, it has many Fourier coefficients. So you say, let's just focus on k equal 1. And then what?
And you have for each cusp form a different Bessel function here.
Yeah.
And you can cusp form by cusp form invert them.
So you're saying I should just take this Q1 of y, expand it in Bessel functions. It's going to have some unique expansion Bessel functions, and then I will determine all coefficients of all cusp forms.
Mm-hmm.
But how do we know that this Q1 of y has a unique expansion in this Bessel function? Because it depends on whether these Bessel functions which have this argument itn, if they form a complete basis, or maybe they form an over-complete basis, and then the expansion is not unique.
Well, the statement is that the thing in the box forms a basis, a complete basis.
Yeah. But now you're talking about this. You're saying let's just focus on the first Fourier coefficients. Then we
Well,
forget
sure.
about cosine. We just look at KITN.
Sure.
So
Yeah.
we don't know what ITN is.
I mean, imagine that you do, because in principle, right, there is a discrete infinity of these labeled by TNs. You know many thousands of them numerically, so imagine that you do. And so now what's the question?
And so you're saying whatever this KITN do, they should somehow form a basis in the space of functions of y.
Mhm.
And that, yeah, I guess. Okay, thanks.
Sure.
Thanks, I see it now. Sorry about
So-
the interruption.
Oh, no, I mean, of course. So-
Eric,
yes?
hi, this is Shuhan. Can I ask
Hello.
a question on this slide?
Yes.
Yeah, so if I take some operator O that's SL2Z invariant, I suppose on a general background, this correlation function of O might still not literally be SL2Z invariant, but transform under some anomalous space. For example, if I just take the partition function, the Vafa-Witten partition function, if I remember correctly, doesn't that also have some anomalous space under the SL2Z transformation?
You probably remember this better than I do. I think the answer is yes, but what I'm saying just applies to observables which do not have such a phase. So,
but for the partition function, that corresponds to choosing O to be 1, right? This is a partition function.
and you want,
What I imagine happening in your work is probably you choose the 4 manifold to be S4, and we choose some nice operators, and probably those anomalous spaces are not there for the particular background you consider. But I guess more generally, there might be such anomalous spaces, and that makes it maybe ambiguous to do the average over the whole modular space.
I feel in a situation where one should not apply this formalism in those situations because O is not invariant.
But for example,
just-
if I consider Maxwell theory, a free Maxwell theory,
Okay.
and just consider the partition function on a general
Uh-huh.
4 manifold. So that
Mhm.
corresponds to choosing O to be 1. And identity is definitely a good operator.
Mhm.
But even that partition function will have some anomalous space under the SL2Z transformation on a
So-
general 4 manifold.
So in that case, one would better not expand it in SL2Z invariant eigenbases.
Right. So I guess for your observables, you probably work on S4 and choose SL2Z invariant O's, and it's not subject to such ambiguity.
Yeah, just to say it a little different. I mean, such ambiguities are sometimes present. What I'm saying doesn't apply in those situations.
Okay.
It's a,
All right, thank you.
it is a separate question. You know, how many exceptions are there to the statement that an n equals 4 observable is SL2Z invariant? And
I would say most of the observables are not invariant, they would be covariant, right?
covariance is just as good as invariance can be anyway. I mean, if you can multiply by something to make it invariant, then
No, I would say more generally,
maybe
object
not.
will just transform under SL2Z. I mean, operators that are invariant, I imagine are the exception rather than the rule.
I have a
Sorry.
small
No,
comment
I'm
about
the
the
operators. I'll talk about some correlation functions.
just a small comment about the force sphere that Chuhang mentioned.
Mhm.
Also on the force sphere, it's a section. It's not invariant even on the force sphere.
n equals 4.
Yes, you get the exponential of the Keller potential, and there are holomorphic transformations from patch to patch.
Yeah,
Um,
yeah, that's exactly what I was wondering
Right. So
about.
yes,
uh-huh.
if you consider these derivatives of the log, right, then that goes away. That's an SL2Z invariant thing to do. What you're describing
Yes.
as these phases.
Yes,
So
indeed.
don't apply this to that observable.
Yes.
Yeah, I also have a comment about what Shu Hang said. I think Eric's considering normalized expectation values.
Ah,
so I
great,
think-
Silvio, thank you. Thank you. Yeah, that's exactly what I was curious about. Thank you so much.
Sure.
Okay.
Let's see, just to make sure I understand. I wouldn't say I'm considering anything specific. I'm laying out a formalism that one can apply if one can construct an SL2Z invariant observable. There are, of course, many of these. And I'm not trying to classify a sense in which some, most, all observables are in this class. However, what I'm trying to say is that because the theory is so invariant, in the, if you will, colloquial sense that when you have a well-defined observable, it is invariant in the sense that the theory is. Of course, one shouldn't take that literally true for all observables for reasons that we're talking about here. Then you can apply these techniques. So something like the lowest dimension in a sector of fixed quantum number or a correlation function of short operators is one such quantity. But some of the things that you're raising which are interesting are not.
Okay, thank you. Thank you.
Yeah, thanks for the discussion. Good. So, all right. So this slide's been up for a while, even though I didn't say the main point. By now, you've stared at it. Because of n equals 4 supersymmetry, the Poincare metric is exactly equal to the Zamolodchikov metric. So actually, the modular average is equal to the ensemble average. And because the modular average appears in the spectral decomposition, it's equally interpreted as the ensemble average, which is interesting. All right. Wow, so we're already 30 minutes in. Very well. So this is a summary of the point of view. Good. So before we move on to understanding some more of the general formalism, I want to talk a bit about this integrated correlator, which was introduced first, to my knowledge, by Binder, Chester, Pufu, and Wang, who studied it from the localization point of view and at large N. So this will turn out to form a really nice benchmark for our methods. So what is this curly G of N? It's a space-time integral of the dynamical part of the 20' 4-point function against some explicit measure, which I'm not writing, which preserves supersymmetry. This also can be expressed in terms of this mass-deformed free energy, and therefore can be computed systematically from that integral. Doragoni, Green, and Wen conjectured an expression for all n and tau. That expression is in the gray box. It takes the form of a lattice integral. So there's a two-dimensional lattice sum over a one-dimensional integral of this exponential factor, weighted against some rational function of the integration variable b sub n. I just want to take a moment to say, I think this expression, this paper is maybe underappreciated. It's remarkable to have an explicit expression for all n and tau, which doesn't grow, the size of which doesn't grow with n. So I don't know of any other object like this, even in n equals 4, where we have something so explicit. So I think this is worth studying more. Okay, so close sidebar. This is manifestly SL2Z invariant. And moreover, the values of this observable for different n are related by a remarkable equation, which relates the action of the Laplacian on the left-hand side to a difference operator acting on n on the right-hand side. There's also a formal representation. Yeah.
How explicit is the formula for this rational function? It's really known, very explicit. You didn't give it.
Good. So for SU2, it is very simple, and then for higher n, you iterate this recursion to get it. The degree of the numerator and denominator is controlled by n. It's linear in n. So yeah,
Thank you.
the numerator is expressed in terms of Jacobi polynomials. It's rather explicit. There's also another formal representation I've given here on the bottom in terms of a sum of these Eisenstein series. This doesn't converge everywhere in the upper half plane, but it is simple and sort of nicer to look at, and will be useful for us. So this is a conjecture. It raises many questions: why this expression exists, how general it is, whether it can be proven. what this rational function is physically, whereas in their calculations, it just kind of pops out. And we'll address some of these in turn. But let me just state what this looks like in the spectral decomposition. So the claim is that this integrated correlator is given exactly by this expression. We have the constant term, n-1/4, and the Eisenstein integral, where the integrand is pi over sine pi s times these same cs coefficients that appear in this last line of this slide. For SU2, it's just this polynomial, and the higher n are fixed by the recursion. So this we claim is the complete expression for all tau. And let me highlight a couple of features of it. First, note that the cusp forms are absent. And second, this constant term is the ensemble average of this quantity.
Sorry, Eric, can I ask a quick question?
Please.
The recursion relation was second order recursion, so it needs two initial conditions. What are those?
Right, good. Yeah, you need CS3 as well then, which is just a sextic polynomial.
Got it, thank you.
Yeah, sorry, indeed. Good, thank you. So this is quite simple and functionally simpler than this. And we know such a decomposition exists. In this case, it seems very easy to write down, of course, given their explicit expressions. Okay, we'll come back to that. So now onto the general analytic structure of n = 4 observables in this spectral language. And I should say, because this is the Bootstrap talk, I'm going to linger a bit on some of this formalism, which I think is very nice. But if I can't talk about that here, then where can I talk about it? With that said, please, if you have had enough and you want to get to the holography side, you can raise your hand and tell me to hurry up. Okay. So in a mode expansion, this is what O looks like. I've just inserted the Fourier decomposition of the Eisenstein series, and then there's the cusp part. So for the physics problem at hand, we want to understand what these overlaps are constrained to look like. So in particular, let's ask the following two important questions, which are a good place to start. First of all, how does weak coupling perturbation theory work? And second of all, how does perturbation theory constrain the overlaps? Note that perturbation theory is insensitive to the cusp forms because they decay exponentially at the cusp. So to answer the first question, well, perhaps it's obvious. All we care about is the zero mode. Non-zero modes also decay exponentially. So we have this top integral. To develop the large Y expansion, we deform to the left and we pick up some poles of the overlap. Now, the asymptotics of the resulting perturbative series should then be encoded in the large S, or rather large negative S, asymptotics of the Eisenstein overlap. So in light of that, how does perturbation theory constrain the overlaps? Well, the perturbative expansion needs to only have positive powers of g², and it cannot have logs. And so the most general form of the overlap in this physics problem is the following. There's a perturbative piece and a non-perturbative piece. First, let's talk about the perturbative piece. We have this pi over sine pi s, and there's an s, 1 minus s there for convenience. And there's a function fp of s. So the poles of the sine generate perturbative terms, and the coefficients of the expansion are encoded in the residues of fp. In addition to this, you can have a regular term, fnp, which gives non-perturbative terms at large y. These are instanton, anti-instanton corrections. So having packaged the poles into this sign factor, and only the sign factor, where we need simple poles at these integer values, one can refine the analyticity properties of fp and fnp a bit more. So to be explicit, by modularity, they have to be even or reflection symmetric under s goes to 1 minus s. They have to be real, so the perturbation series gives something real. They have to be regular everywhere away from s = 1 and its reflection. S = 1's a little funny point. the total overlap has to be finite there, but FP and FNP can have poles that conspire to cancel. A small point we'll need later is that at s equals a half, the overlap has to actually vanish. Why is that? Well, the Eisenstein series itself actually vanishes at s equals a half. And finally, if one of them is 0, then it follows from everything I've set up here, 1 through 4, that the other function is entire. Okay. So given the 0 mode, say if you know the perturbative series, or you just have some access to the 0 mode somehow, there's an explicit algorithm for getting the other modes modulo cusp forms. You take the 0 mode, you integrate it to get the overlap, and then you plug the overlap into the decomposition and just insert the kth Fourier mode of the Eisenstein series. And this gives you the kth Fourier mode of O up to cusp forms. As we stated before, if you have an asymptotic series, or you have a series rather with a given asymptotics, then that's encoded in these residues Fp as follows. Right? So Cn are the expansion coefficients of some perturbative series. They're related to the residues of Fp after you account for the form of the 0 mode of the Eisenstein series by this way in this equation on the right. And so at large N, where you address the asymptotics, the convergence, divergence, etc. of the series, you see that if there's a sort of radius r, for example, if the series is asymptotic with factorial growth and some parameter r here, then Fp in turn divides by that factorial growth and this pi to the minus n to give an r to the minus n scaling. Okay. So let's revisit the integrated correlator for a moment in this language. So it's even simpler than we said before. Okay. So the cusp form overlap vanishes. The non-perturbative part vanishes. And the perturbative part, of course, is non-zero, otherwise the function would itself vanish. And for SU2, it's just 2s minus 1 squared. And so the way I want you to think about this, and I mean this in a sort of uncontroversial way, hopefully, is that the integrated correlator is literally the simplest SL2Z invariant observable in SU2 super Yang-Mills. So here simplest means something very elementary. We have these 3 functions. 2 of them vanish, the more complicated ones vanish. The remaining piece, by way of the constraints I articulated earlier, has to be a non-constant entire even function of s minus a half. What's the simplest function? It's the degree 2 monomial. And this observable, since it doesn't depend on anything else like cross ratios, it just depends on tau. That means that Fp is just dependent on s, no auxiliary variables. And so that's very nice. So this thing is even simpler than we thought. I wonder what the integrated octagon looks like. The octagon sort of previously had the claim of being the simplest observable in n equals 4. And perhaps it is if you allow dependence on cross ratios or other variables. But this thing, you might say, is even too simple. But I'd be curious to know what the integrated octagon looks like. And by that, I mean the integrated 4-point function, which in the large n limit becomes the octagon squared. Okay.
So Eric?
Yeah.
How do you know these properties of the integrated correlator? They follow from localization, or they follow from this conjecture?
Oh, they follow from the Storgoni, Green, and Wen paper, where so we're taking their expressions. So for SU2, they have this conjecture for general n, but for SU2, it's from the localization integral. That's the source of the data which allowed them to make this conjecture. They write down an expression, and you can convince yourself that it's true because of the strength of the data that they use. So given what they wrote, we are restating it in spectral language, and you find that it ends up boiling down to this.
Okay, thank you.
Sure. Now, typically, the weak coupling expansion in n equals 4 super Yang-Mills is asymptotic. So recall this relation from before. So we want to Borel resum such an asymptotic series, and it will be interesting to define what we call the SL2Z Borel transform. B of Xi is given by the original sum where you divide the coefficient Cn not by the usual gamma function, but by this completed Riemann zeta function. Remember that this is basically of the form gamma function times zeta function. But this lambda factor is what appears universally in SL2Z invariant perturbation theory. So dividing by this gives you especially nice results, and it may be neatly inverted, giving the desired resummation of the original function O, by using the fact that lambda is the Mellin transform of the Jacobi theta function. This is a specific modified Borel transform tailored to the SL2Z case, and it has various nice properties that follow from the SL2Z invariance itself. So there's an inversion symmetry on the bottom left. There's the fact that this integral vanishes. So the residue of, sorry, I didn't define RS here. That's the overlap of O with the Eisenstein series, also known as the Rankin-Selberg transform. Sorry for the notational flub. So this integral of B weighted by 1/(x) to the 3/2 vanishes. And lastly, the thing on the right shows that the ensemble average can be neatly written in terms of this SL2Z Borel transform. Okay, so note as a side note that this middle relation implies that B must have a 0. I wonder why. The physics of when Borel transforms have zeros is, to my knowledge, not very well understood. There is a paper by Masazumi Honda thinking about this in the context of 3D superconformal theories, but it is in general an open question, and we see it is necessary in this SL2Z case. That deserves more thought. So with this in place, we can return to the question of the redundancy of instanttons. So we recall this algorithm, and naively, this implies that the kth instantton perturbative expansion is Borel summable if the 0 mode is. After all, it's determined in this nice way up to Cusp forms. Okay, but actually it's not obvious. And to appreciate why, let's look at the Fourier decompositions. If you look at the second line, then you see that every such Bessel function contributes to every power in 1/y. So you need to be careful in asking what is the coefficient of the y to the minus n term in the non-zero instanton sector. Whereas in the first line for the 0 mode, only a single pole of the overlap contributes. But it turns out to be true. And the result ends up being very neatly phrased in terms of the radius of convergence of the SL2Z Borel transform around k instantons. So there's an extremely simple relation between the convergence radius in the k instanton sector, defined to the left here. So if I take the Borel transform of the k instanton mode, and I define a radius r sub k, then r sub k is given by the radius in the 0 mode sector, which I call r, times this extremely simple function, 1 plus k over r squared. So this is striking evidence of the redundancy and the simplicity that I was talking about. Here, this is modulo Cusp forms. That's important, but it can be generalized using some number theoretic properties of the Cusp forms. Unfortunately, in view of time, I think I'll skip that slide, but good. So one more slide, then we return to the integrated correlator, then we move on. So in fact, again, when the Cusp form overlap vanishes, you can reconstruct O from its 0 mode as a Poincare sum. So sum over SL2Z images of the 0 mode of O. What do you get? You end up getting this expression in the box. Now this probably looks familiar. Let's go back to the integrated correlator. We've now been able to explain the form of their formula. Their formula is just the Poincare series representation of the integrated correlator. And this kernel Bn is just the SL2Z Borel transform of the 0 mode. All of these relations here were observed in the paper by Doragoni et al., but they follow just from basic relations that any SL2Z Borel transform has to obey. We can also check this result for the k instanton radius of convergence. Indeed, G sub n is asymptotic but Borel summable in perturbation theory. So this relation predicts Rk equals 1 plus k squared, because you can easily read off from the 0 mode from their explicit expressions that R equals 1. So how is that realized? Well, it's realized if you look at the explicit expression for the kth instanton mode. It's realized as the maximum of p plus q squared, where p plus q are positive integers whose product is k. And this is indeed 1 plus k squared, which is nice. Okay, so skipping that slide. So what did we do? We introduced the big tool, which was the spectral decomposition. We explained why n equals 4 observables admit 1, and we constrain their overlaps by demanding the existence of a good perturbation theory. And then we introduced some assortment of smaller tools, which helped us see through to the simplicity in instanton physics, and went back to this integrated correlator and explained the form of the result in a very physical way. So are there any questions before moving on to large N? Okay. Bonus slide. Yeah, we're gonna have to skip this in view of time, but come back to it at the end if you want to know about it. This is about the extremal n equals 4 theory. I'd be happy to answer a question about that at the end.
All right, sorry. Can we not skip it?
Sure. You might be disappointed at the result I have, which is not really a result. It's just the comment on the question. Okay, but yes, this is the crowd for this slide. So here we go. There's this question: are all unprotected operator dimensions maximized at the corner of the fundamental domain? In other words, where is the extremal n equals 4 theory on the conformal manifold? The spectral method is not obviously well suited to prove or disprove the conjecture. So let me demonstrate why with what's on this slide. The main statement is that the spectral decomposition involves the Eisensteins and the Cusp forms, and the Cusp forms have sporadic locations for their global extrema. And the extrema have magnitude which is not small compared to the Eisenstein series. So for example, here's a plot from a paper by Hedgehall and Rachner with many other nice plots of a Cusp form with spectral parameter about 500 for some portion of the fundamental domain. And I've plotted the location of the minimum and the maximum with the minus and plus respectively. These are at what you might call random location from the point of view of a conformal field theorist. Okay, and if you look at other Cusp forms with t equals not 500.283548, but t equals 500.283546, or whatever the next one is, they'll be somewhere else. So in general, the Cusp forms and the Eisensteins will compete. And so this treatment of SL2Z seems insufficient to prove or disprove the conjecture, and maybe even cast some doubt on its validity. But it does shed some light. So you can show using the techniques I described before that if you have some Borel summable observable, as one typically does, then the overlap is bounded at large values along this critical line, and it decays exponentially at large t, where the index of the Eisenstein is a half plus it. So let's for the moment assume that the extremal theory lives either at tau equals I or tau equals omega, which is equal to I pi over 3. The conjecture then hinges, at least in the Eisenstein sector, so ignoring Cusp forms for the moment, on the following question. Near the origin in t, before the exponential fall off kicks in, where is the Eisenstein series larger? Is it at tau equals I or tau equals omega? And the answer is tau equals omega. This is not supposed to be obvious by thinking about Eisenstein series, because on the critical line, these are wild objects. They are basically like the Riemann zeta function. And indeed, at tau equals I, the Eisenstein series has an expression in terms of Hurwitz zetas. And Hurwitz zeta is an argument a half plus it. Well, that's where the non-trivial zeros are. Okay, so this is definitely not a trivial thing to see. So what if I plotted here? On the left is an example of this exponential decay I'm talking about. The more interesting plot is the one on the right. So here I've plotted the real and imaginary parts of the Eisenstein series with index a half plus it. The x-axis is t, and two of the lines are at tau equals I, and two of the lines are at tau equals omega. The blue and orange are tau equals omega. The green and red are tau equals I. And so the fact that the blue and orange lines are have greater amplitude than the others for these values of t close to t equals 0, here I've plotted out to t equals 5, ends up being the statement that when you multiply against the overlap, tau equals omega wins. So for example, on the left, this function decays very strongly all the way, right? When you're at t equals 2, it's already decaying exponentially. But the Eisenstein series at the corner point is greater than the tau equals I Eisenstein series in this range of t and beyond. So to definitively, analytically answer the question, you need to have control of these exponential tails and so on. But at least for this, using numerical data about the locations of these zeros combined with the exponential behavior, it gives some kind of credence to the conjecture that the corner point is the extremal point. But
so one word about this conjecture. I'm not sure if anybody ever made a conjecture that all operator dimensions are maximized. We only talked about the leading edge trajectory.
Okay, duly noted. I'm
actually not even sure what you mean for all operator dimension to be maximum. We're just talking about the leading edge trajectory in the 4-point function of 20 pi.
Sure. Okay. I thought Alday and BZ made the stronger one, but that might be wrong. I don't want to slander. Of course, it could be right, and then they should get the credit. Yeah, I mean, actually, I'm wondering why you say you don't know what I mean. That all such dimensions could be maximized. Is there some obvious reason why not?
Clear what? Well, I don't know. You want to order you need some ways to order the operators, right? I mean, I suppose you want to say that for the leading edge trajectory, it's very clear what the operators are. Above that, don't things get a bit ambiguous? I don't know. Maybe not.
Yeah, I agree. I agree with that set of mumblings. Yes.
Yes.
Yeah. Good. Okay.
Can I ask another question? So do we have any evidence of any observable in n equals 4 where we know that these cusp forms must be present?
Yes, so there's this other integrated correlator that has been studied recently by Shai and Silvio and friends, and also so that one, despite also being supersymmetric, does have cusp form overlap. Scott and I took the expressions at large N that were derived by these other authors, rewrote them in our language, and observed that there are cusp forms there. So you might be familiar with this solution to this inhomogeneous Laplace equation, this generalized Eisenstein series that appears in the 1/n expansion of this object. It's the same thing that appears at the d⁶ out of the 4th level in the type 2b string action. That function admits a spectral decomposition after some subtracting of power law divergences. And so that thing has a cusp form overlap. And so that anything that has a d⁶ out of the 4th contribution at large N, at least in that large N setting, has cusp form overlap.
Thank you.
Sure. I would say in general that you should expect the generic observable to have cusp form overlaps. I don't see why not. And so that's a blessing and a curse. It's a blessing because these things are chaotic, and that's interesting. It's a curse because they're chaotic, and that's hard. But maybe, as we can talk about at the end, the combination of numerics at small eigenvalue and universality at large eigenvalue might be useful for some kind of bootstrap approach. It's not all hope is lost. Okay. So how much time do I have?
We started a little late, but as far as I'm concerned, there were also tons of questions. So let's say at least 15 minutes.
Okay, thanks. All right, onwards. So at large N, we'll just talk about the TUF limit today. There's this other very strongly coupled limit of large N and fixed G-Yang-Mills. But today we'll just talk about the large N fixed lambda limit. Observables admit a genus expansion of this form. You can think of this as an expansion just of the 0 mode because non-zero modes are suppressed non-perturbatively in N. because they go like e to the minus y, and y is n over lambda, and lambda is fixed. Okay. So what are we going to do? Well, the prescription is clear. Develop the 1 over n expansion of the spectral overlaps, rewrite the Eisenstein series in terms of n and lambda instead of y, and plug them both into the spectral decomposition and see what you get order by order in 1 over n. For example, for reasons I won't explain, the 1 over n expansion of fp can be shown to take the following form. There's a sum over genus, and then there's an n to the minus s times some function fp of g, the genus g part of fp, with argument 1 minus s in our conventions. There's also the reflected partner, because this thing has to be reflection symmetric. That'll be important in a moment. And for now, we'll take fnp to be 0. This will actually make it easy to infer the consequences of non-zero fnp, and ultimately we'll restore it. The power of the formalism in the TOEFL limit is actually pretty easy to see. So here's sort of a toy model. It's essentially the full expression. I'm just suppressing some coefficients. An expression for the 0 mode of O in the TOEFL limit. There's the constant term, the first guy, the ensemble average, that is a constant, so it contributes to the 0 mode. There's the sum over genus, and there is the spectral overlap, and there are 2 types of terms. Okay, so there's the pi over sine pi s, s1 minus s, and the stuff that's important is in the parentheses next to that. The first term looks good. That'll give you the usual lambda dependence of your observable. But there's the second term, which must be there by SL2Z invariance. It's a combination of the Eisenstein Fourier mode and the structure of the spectral overlap that I wrote in the previous slide. It looks a little strange at first. You have explicit powers of n, and there's an s in the exponent. So if this is to be consistent with the genus expansion, first of all, because we're doing a large n expansion, we have to deform it to the right. And if it's to be consistent with the genus expansion, then this fp function needs to have poles to the right of s equals a half, only at half integral locations. That'll give us powers of 1 over n squared, 1 over n to the 4th, and so on. Anything else is inconsistent with the genus expansion. But you see, that's already interesting, because it's the same function which, at strong TOEFL coupling, when you deform also to the right to get the first term, tells you where those poles are, right? It gives you the powers of lambda that you're allowed to get. So the strong coupling expansion, when fnp is 0, is only odd half integer. So you immediately learn that if you have some quantity at strong coupling where there's an integer power of 1 over lambda, then the non-perturbative part of the spectral overlap is non-zero. The fact that these powers of n are appearing at fixed genus is also interesting and kind of strange. So SL2Z rearranges the 1 over n expansion in the sense that, say at fixed genus, say genus 0, there's an n squared in front, but there are these subleading pieces in 1 over n. And what this is telling you is that you should think of them as a kind of renormalization of the genus 0 answer. They come with positive powers of lambda. So after you do this deformation, you pick up some poles. So the first term in this final expression skews the lambda tildes, and these r's are coefficients, which I'm not going to define. They basically are the residues of the integrand above. It's not so complicated. The first term again gives you what you expect from the large lambda expansion. The second term are these renormalization terms. So how do you think about this? Let's take an example. The genus 0 m equals 1 term gives you an n to the 0 root lambda contribution. This is what happens when you do the 1 over n expansion at large lambda. At first subleading order, you get a term that goes like root lambda. That's large, so you need to renormalize it away. And in the bulk, this is what the 1 loop r to the 4th term in type 2b string theory is doing. It cuts off the divergence of 10d supergravity at the string scale. And in the CFT side, you just see a term like that appearing in your 1 over n expansion, a large lambda. And SL2Z is packaging this for you in such a way that the higher genus terms are not polluted by this divergence. The third thing I want to point out about this expression is that if there are non-perturbative effects at large lambda, then there are non-perturbative effects at large n. In other words, non-perturbative effects in large n. Why? Well, both are controlled by the same asymptotics of the same function. So if I look at large positive S, that'll tell me whether I need instanttons controlled by some power of lambda. But then there's the second term here, the SL2Z partner, which will give me instanttons controlled by some power of n. Now, with a technical assumption, you can infer the following picture. It would be nice to prove this in general, but it's borne out in examples. If you have a convergent weak coupling expansion, then you end up getting a non-Borel summable strong coupling expansion with the need for non-perturbative corrections. So what is the picture? We have some zero mode as a function of lambda. We have a sum over genus, and there are two types of terms here. There's a function of lambda, which is the first term in the box, and at large lambda, there are perturbative pieces, say the little n equals 0 part here, and then there are instantonic pieces that go like powers of e to the minus 2 pi root lambda over root lambda star. Lambda star is the weak coupling radius of convergence. The fact that that is appearing in this strongly coupled non-perturbative sector is an interesting consequence of SL2Z that I tried to briefly explain, but it appears in this way, at least under a certain simplification, which seems to be true. Generically, lambda star is pi squared in planar n equals 4, so you can think of that as just some number. But in addition to this, there's this other piece.
Sorry, how do we know that it's pi squared?
So generically, this is something that follows from the Magnon dispersion relation and is often quoted in these integrability papers. This is more of an empirical observation for me, but it seems to be true that absent some extra protection by some symmetry, the weak coupling expansion at small lambda and the Toff limit is convergent with radius pi squared. But yeah, for that reason, we left the lambda star dependence explicit. Okay. But then SL2Z tells you that there's also this other set of terms, which takes the same form, except instead of what you can think of as an S-dual Toff coupling. So this is n squared over n over g squared. But they're present in the Toff limit. But in the Toff limit, this is non-perturbative in n. Right, lambda is fixed, n is large, but you can think of this as being packaged in terms of an S-dual Toff coupling. And when you do that, it reveals quite cleanly what is happening in the bulk. What are these non-perturbative scales? Well, taking lambda star equals pi squared, just to simplify things, these instanttons proceed in powers of lambda, large lambda squared, where on the one hand, you have this fundamental string instantton scale, and on the other, you have this d-string instanton scale. So SL2Z is telling you something that seems very natural from the bulk point of view. If you have fundamental string world sheet instantons, then you have d-string world sheet instantons. More broadly, if you want to know, does the perturbative string expansion in ADS5 times S5 converge? Well, what this result suggests and shows in certain explicit cases, which you can confirm, is that it's completed either by space-time instantons, which would be terms coming from FNP, d-string instantons, which are non-perturbative in the string coupling, or both. We did some explicit computations of these corrections for the integrated correlator. They end up taking a relatively nice form. And when you turn on this FNP, whether the non-perturbative effects are there can change, but if they're there, the non-perturbative scales are the same, and SL2Z insists on there being both. Okay, so let us move to the supergravity part. And what I'm about to say might already have been obvious from the expression I flashed before in the Toff limit. So let's go back to that for a second. Okay, so let's look at this expression. There's the ensemble average piece, and then there's the rest. If you want to expand this at large lambda, the first term would give you negative powers of lambda. And the second term would give you negative powers of n. So that's suppressed compared to the leading n squared term. And that's interesting because it smells a lot like the usual strong coupling expansion, but it's different. If you include FNP, then the story generalizes, and you find that assuming the observable O starts at genus 0 for simplicity, that is to say it has an order n squared contribution, that at large lambda, the expansion takes the form n squared times a constant plus the usual subleading corrections in lambda. But the constant is just the leading term of the average, the n squared part of the average. So you immediately conclude that at strong coupling, O turns over to its average. Of course, this is just the supergravity regime. So you can equally phrase this as the statement that the large n limit of the average is equal to the value of the observable in supergravity equivalently at strong self-coupling. So back to this picture, on the right is the conformal manifold averaged at some fixed n, and you take the large n limit. And on the left, you have the conformal manifold where you haven't averaged. You've just gone to the strongly coupled point at large n. And these two things are equivalent at the level of these observables O. Some comments. At risk of stating the obvious, let's just rephrase this in bulk language. So the ADS5 times S5 supergravity is both a low energy limit of classical type 2B string theory on the one hand, and the classical limit of the average over the type 2B moduli space on the other. Now, I'm not claiming that the usual holographic correspondence is somehow invalid. That still holds. The statement is just that at strong coupling in large n, there's an emergent ensemble average, which is equivalent to the strongly coupled theory. So in this large n regime, averaging generates a simple bulk dual, just like it does in these lower dimensional examples, where averaging is really at the center of the duality. And indeed, it's the extremal theory that one gets that's consistent with the symmetries being imposed here, that is to say, the strongly coupled theory. It also suggests what I think is actually a plausible new strategy for deriving ADS5 supergravity from CFT, which is instead of trying to obtain control over the large n limit at finite lambda and then taking the large n limit, which is, a hard problem, although of course integrability helps us there, compute ensemble averages and then take their large n limits. These two things are equivalent. And in the case of Narain CFTs in 2D, there's some precedent for the possibility that you can compute the average, say, of the spectral gap, but you can't actually explicitly go out and verify this or, on a case-by-case basis, compute this gap. But knowing the average is enough to make certain statements. And it seems possible that if we can develop a theory of ensemble average quantities in n equals 4, that their large n limits, therefore, would give us the supergravity results, and therefore we can comprise some kind of holographic derivation of the supergravity value without actually having to contend with the strongly coupled physics per se. To be clear, this is just an ambition. The last comment about this is that the result extends to all orders in 1 over n. So if we define the large n limit of the genus G part of the average, so take the average of the genus G part of O, and then strip off the powers of n, then the spectral decomposition spits out the most general strongly coupled expansion, and it's of this form. So it's just like it looked before, except now I'm including renormalization terms, but at every genus G, they are down compared to the average. So you again have the statement that the genus G part of O at strong coupling is given by the genus G part of the average. The fact that this is possible, it's interesting that it uses, crucially, the fact that these renormalization terms are being packaged in this way, because, for example, the n to the 0 piece of O only makes sense if you can get rid of the root lambda part. And this formalism is doing that for you. And once it does that, right, this double bracket OG, that's a finite, that's a number. That's just the coefficient of say n to the 0 at genus 1 and the average. And so that's a number. So this is telling you that somehow loop level supergravity with a certain renormalization scheme is being reproduced by the average. Okay, so we're coming up on the end. So let me just make a couple comments and I'll skip to the end and then we can discuss as desired. We studied the SL2Z ensemble, that is to say the space of n equals 4 theories, because the correspondence between the average of O and the supergravity value of O suggests that we should do this. We were able to write down a nice expression for the variance in terms of the spectral overlaps. At large n, the variance is suppressed by 1 over n compared to the squared average. That's actually a bit mysterious from the bulk point of view. We checked this with the integrated correlator. There are also non-perturbative effects. And so this leads directly into a discussion of whether this sheds light in the factorization puzzle and wormholes and so on in the ADS5 times S5 context. We also discussed some possible generalizations of this story to other theories. We can discuss this in the question and answer part, but I don't want to drag on any further. So let me just stop with some future directions. I will take a moment to say some of these out loud because I think I want to make sure some of them get heard. So I think formulating bootstrap questions in spectral space will be profitable. We haven't thought about all the ways of combining this technology with other bootstrap methods. I think we should try to rephrase what we know about n equals 4 in this language and see what comes out. And that the integrated correlator showed that this really, even in the case of something that already was pretty simple, gets to the heart of what an observable is, the non-trivial pieces of an observable. For example, obviously we all are interested in understanding how correlators look in n equals 4. How it plays with this language, I think, would be nice to understand. The arithmetic chaos story is a totally different angle. The holography story is a totally different angle. And now I'm just trailing off. So let me just stop and say thanks.
Thank you. Any more questions?
I have a question. So you mentioned that there are these chaotic things happening, and then, but what I didn't quite understand. So does it imply that these functions that you are going to be expanding in this basis? So the base is chaotic, but does this mean that the functions also, in some sense, chaotic? Because I was wondering, maybe the function itself is just a perfectly nice function. If you just look at it, it doesn't show any chaos. Perfectly smooth function, doesn't have any weird minimum maximum in some random places. But then it's just the basis is fucked up. It's chaotic basis because this number theory comes in. But the function itself maybe is just perfectly nice. Could this be a possible scenario, or you think that somehow the fact that the basis is so weird means that the functions are also going to be weird?
I think it's both. So it's important that the Eisenstein piece is also there. So the way I think about it is that the chaos is kind of hiding underneath. Certainly, if you look at the distribution of conformal dimensions and things that we know pretty well over the fundamental domain, they don't look nearly as chaotic as those plots I gave of the mass cusp forms, right? But that's because they also have this continuous piece too. Somehow there's going to be some chaotic part. And then there's another part which is smooth. What
but I'm trying to make a different point.
I don't know.
It's just, this chaos appears because you choose to expand your function in eigenvalues of Laplacian.
Okay, sure. Mm-hmm.
But what if you didn't expand the eigenvalues of Laplacian? There are many other. So Laplacian is chaotic on a ton of different manifolds.
Mm-hmm. Mm-hmm.
So could one take a point of view that, okay, if the basis is so bad, then okay, let's just not use this basis. Let's find some other basis. Number theorists, they have no choice, but maybe there are other bases which don't show this chaos, or is this like? Where are you saying that?
No, I think I feel this is getting at one of the open questions. Yeah, the sense in which we should really truly think of n equals 4 observables as chaotic or not, I'd like to know the answer. I don't know of any other basis that, I mean, personally, we can use in this setting that gives nice control. I feel the Moss-Cusp forms are telling us something, but it is, even in this setting, pretty obscured. So it's not as if I even picked a basis where the chaos is very manifest. Moreover, I should say that the form of chaos that these cusp forms exhibit, it's called arithmetic chaos because, well, because SL2Z is an arithmetic group, and another way to say that is that there are this infinite set of commuting generators, these so-called Hecke operators, for which these cusp forms are eigenfunctions. So there's a kind of symmetry which is acting here, and that's why it's arithmetic chaos and not something like, you know, GUE RMT type chaos. So even in the world of chaos, it's milder than other things that sometimes arise. But it is arising, so I think we should try to understand why.
Maybe you said it already, but just to make sure I understand. So if you take one of these Eisenstein series with a real coefficient, like 3 halves or 5 halves, the ones that appear in the scattering amplitudes context, yes. Right? In string theory. So these ones, they have a kind of they have expansions which include both terms, both the cusp forms and the continuous part. Is that the statement?
But those Eisenstein series, you're asking, do they have an expansion which includes both of these parts?
Yeah.
No. So those are not square integrable. So what happens with those is that this formalism can be extended to include functions which are not square integrable but have power law divergences. And the way one does it, so in order to preserve modularity, one needs to subtract out these terms which diverge at the cusp in a modular invariant way. And what one does is one subtracts Eisenstein series for every such term. So you should really think of these Eisensteins with real index greater than 1/2 as having 0 spectral decomposition upon regularization.
So then I didn't understand what you said. There is something that appears that has a cusp form. It's not one of these. It's something more complicated.
No, so it is exactly. Sorry, it's not one of those. It's something slightly more complicated, but in the same class. So in the 1/n expansion, so the thing I was referring to is not the coefficient of r to the 4th, but of d to the 6th r to the 4th, where it's a solution of this Laplace equation with a source term, which is the square of E3/2. So it's Eisenstein-like, but not quite. But in the 1/n expansion, order by order, the coefficients are not square integrable. So you get E3/2, E5/2, this funny thing. So in the 1/n expansion, you can have that happen. So my statement before about the cusp forms was taking some quantity and expanding it large n, for say this other integrated correlator, we see that the cusp forms turn on at some order in 1/n. And therefore, in turn, at least for some range of finite n, the cusp form overlap is non-zero. Otherwise, the large n limit would trivialize. So that's how I was thinking about it.
Thank you.
Sure.
So I had one more question, which is if you go to this idea that at large n, large lambda, you get the ensemble averaged answer, where you have, which you pictorially have very nicely drawn this. It's like you have this moduli space and you get the ensemble averaged answer at finite n, sorry, at large n and large lambda. But if you take any other point, I mean, is the answer constant over the moduli space at large n? Do you not? So if I take not lambda to infinity, but G finite, right? I don't go to the weak coupling. I mean, lambda to infinity is still sort of weak coupling, which you indicated here. But if I go to strong coupling and then large n, do I get a different answer?
Yes. So,
So it's really
well,
just an
sorry.
average.
So it's a little hard to answer that. Right. So you're imagining, say, taking the very strongly coupled limit of large N fixed G,
Yeah.
and asking, as you vary G, how far do you get from the average?
Yeah. In other words, in the left picture, can I move that point somewhere inside M? And not,
Yeah, you basically can, because in that limit, say thinking about the bulk action, observables take the form. So the leading term. So if you take that limit and then you take G to 0. The leading term is again supergravity. These two limits match. But for finite G, you get supergravity plus 1 over n, powers of 1 over n times functions of G, like Eisenstein series. But they are suppressed by 1 over n.
right.
So to leading order in n, you do just get the supergravity answer even in that limit.
Yeah. So in some sense, it's kind of constant on the moduli space, right?
Yeah, so I think somehow the large N limit of the average, sometimes I get asked what part of the moduli space is dominating the average or something. And so somehow large N, if you think of this at large but finite N and small but finite G as some good approximation of strong TÜV coupling, if you increase G, you're only increasing lambda. So most of the moduli space is strongly coupled in this kind of casual, illegal sense. But I think morally that is somehow capturing some of what's happening. I phrase it in terms of the TÜV limit because it's more familiar to all of us that that's the supergravity limit.
Sure.
Another thing to say about that is that the large N limit and the ensemble averaging don't commute. Exactly for the reason I said before, that the coefficients order by order and 1 over n are not square integrable. So if you take the large N limit and then average order by order, you will get infinity. And if you try to regularize in a conventional way, say by subtracting Eisensteins, as is typical in this setting, you get wrong answers still. So it's a bit of a dangerous game. I think there's, in some sense, you get the right answer because of what I just said, that the leading term in n is supergravity and everything else is down in powers of n. But it's less well controlled. So I think you really should think of the average, taking the average at finite n and then taking its large N limit. But I think you can get away with thinking about it that way, and it is useful actually.
I see. Thanks.
Thanks for the question.
Any more questions? I see nobody unmuting, so thank you again, Eric, for a very nice talk. And I think we can stop the recording now.
I have to do that, right? Stop recording.